All right, so here we are today reviewing for tomorrow. Well, for you guys, it's not a quiz, but we're going to have a quiz. All right, so you guys are in school today, so you're going to have your quiz Thursday. So you're home tomorrow studying, guess having extra time. But so my kids that are home today are taking the quiz tomorrow. And so the quiz is on everything that we've done so far, redox in general, but basically it's based upon the Voltaic cell. And a great way to study is to take, for you guys, I gave you guys a blank copy of the homework we've been working on the last couple of nights over the weekend. And that homework's a great example of what you're going to see, the first side or the second side. And I'll talk about the individual components and go over it completely. So you know, on the bottom of that, Christmas in July, right there, the Tuesday homework, I have nothing new. Here are some things you have to be able to do, okay, for that quiz. The best way to study is to, I think, redo these. And for those that are home, you could certainly do what? You could certainly just print these out and redo it. You say, well, I did it once. Maybe you forgot, okay, and do it from scratch. And we'll be doing pieces of that this period to review. Okay. And for those that are concerned, everybody who takes a quiz from me is going to have a folder. That folder, you're going to have a full complement of reference tables. You're going to have the AP reference tables that I give you. I'm also going to give you the Regents reference tables, like table FUFU, table F, that you're going to need to know in terms of solubility, whether ions, whether a salt, an ionic compound, and a crystal breaks apart into the ions based upon Coulomb's law. So all that stuff is available to you if you're viewing pleasures and quizzing pleasures. Your quiz also is a quiz, just like your forms, but this quiz in class that you're going to take Thursday will count 3 times, okay, a regular form. All right, and again, and also you'll get it back probably Thursday afternoon or evening, meaning I'll grade them, scan them, and email them back to you so that everyone gets them back pretty fast. The guys who take it and gals who take it tomorrow will have to wait till Thursday afternoon because I don't want to be having answers all over the place. All right, any case, let's get started. So, party people, let's continue and let's go with, I'm going to start with Le Chatelier's principle. Right now, you have this worksheet. It's the back side. I didn't ask you to do the back side, but I want to start our discussion today or review with this problem, okay? And that's what I'm doing. Guys, you're so loud. Calm down. Big class here. All right, now, what happened here? Okay. So here's our reaction. Double arrow means equilibrium. Okay, so what does this mean? Okay. That's bugging me out. Okay, so here we go. Every time I touch this, it does it. You just stay there? Okay. So here is the reaction, or the physical process. It's not really a chemical reaction. Okay, every time I turn around, it's sticking in. Okay. Now, so what I have is silver chloride. That was doing so well. Is it this one? Silver chloride. Solid. Breaking apart into its ions. Ag plus and Cl negative. Okay. What's happening? I'm not even seeing it happen. Okay. All right, so there it is. And this is solid breaking apart to aqueous. It did it again. Okay. And it's a double arrow, which means it's in equilibrium. So here's what it really is, or what it is in real life. We have this beaker, not with black water, but we have that. And we have a precipitate. We have silver chloride. Because I'm artsy, I'll draw it to the side. And that's AgCl. All right, if you're taking a picture, it would be artsy, just tilt it, I guess. I don't know. All right, but what is AgCl? Hey, that's a metal. That's in this area. Big. Chlorine's a nonmetal. Small. Hey, when those get together, there's a transfer of electrons and you make a salt, an ionic compound. Party people, we're dealing with this, okay? A crystal. Even though they write Ag and Cl, don't let it fool you. We're talking about something that's sticking together. They give you a chemical formula of the lowest ratio. So I'm going to write it here. Really, it's Ag plus attracting Cl negative. This is attracting Cl negative, and this is Ag plus. And it goes on and on and on in all directions, but the bottom line is there's one Ag plus for one Cl. That's what gives us the chemical formula AgCl. This is an ionic compound. Okay. Now, double arrow means an equilibrium. Equilibrium means that the forward rate and the reverse rate have the same directional pathway. In fact, because they have the same pathway, this is the death of the reaction, right? If we were to draw a U diagram, hope you get it. This is equilibrium. There's no preferred pathway on the bottom. And this is our reactants, 100% products. And the forward process means that solid breaks apart into Ag plus and Cl negative. Because we're at equilibrium, which means there's no preferred pathway, that means that as fast as these guys make silver chlorides, these guys come together right now and reform the precipitate. They go backwards to reform the precipitate. I'm writing this this is getting bigger. So a piece of this gets smaller, become ions. They're flying around the water. We know better. It's not really silver by itself. Silver plus is being encircled by the negative part of water. Famous boyfriend, famous girlfriend scenario. And the chloride ion is being encircled by water, by the positive part of water. The reason that it has some solubility is water can compete with these charges somewhat. Okay? Now, we're in equilibrium as fast as me, so nothing appears to happen. The amount of silver chloride solids staying constant. Okay, so here's the question. The addition of KCl to this system will cause a shift where? Okay, so we're going to add KCl. Now, the question you have to say to yourself, is KCl part of the net ion reaction? Okay? Now, I'm going to write in red the Danielle Cell. That Danielle Cell, that battery that I keep putting up here and trying to manipulate, sometimes with success, sometimes not. So that battery I keep showing you in class, here was the net ion reaction. I had zinc 0, who oxidized. Copper plus 2 grabbed those electrons in another cell, and it went to what? Zinc plus 2 to copper 0. That's the net ion. There's nitrates in there. They don't do anything. There's electrons. They get passed around evenly. That's the net ion reaction. So is this. And, all right, I'm not showing a double arrow, but I'll keep it there. Now, I did a couple of things to this year. I added water. Okay, I also added different compounds. If I was to add KCl, or if I was to add, let's say, sodium ions, Na plus, to any one of the two beakers in this cell, would it change anything? Is there any sodium in that overall reaction that was in our Danielle cell? You see any Na plus anywhere here? No. It would have no effect. No effect. So it leads probably us to believe that if I add KCl into this beaker, the same thing would also be true because KCl is not in the overall reaction. and you would be wrong. KCl is really what? Isn't KCl an ionic compound? Isn't KCl a metal, big guy, with a small guy? Which means the big guy lost, became positive, and the small one gained, became negative. It's another salt with the lowest ratio. May I ask you a question? Does KCl dissolve? Does KCl dissolve in water? Yes, it does. And for those that forget, table foo-foo is your friend. But you should know that group 1 ions are always what? Soluble. And there's no exceptions for group 1 ions. They're always soluble. And K is an example in the first column. It has a small charge, which means water can get around these and separate. So if I add KCl to this beaker, what's it really breaking up into? Water is going to compete for these charges. The negative part of water is going to start attracting the outermost of this part. And if water starts attracting it and competing for charges, this doesn't feel these negatives anymore. This can pull away. It's going to become K plus, and positive part of water surrounds that, and Cl negative. So party people, KCl in water breaks apart into K plus and Cl negative. So potassium chloride is delivering a soluble ion, or KCl being a soluble salt delivers something that we call a common ion. What is common to this system here, to both? Aren't we really increasing the chloride ion concentration by me adding KCl? You have to be able to identify that, okay? We are adding a common ion. Whether you know it by name or not, we are increasing the chloride concentration. You've got to know that this is really that. You've got to know that solubility is a measure of this system to break apart into free ions. I say free ions, but the water are surrounding them. So, now that you have identified that adding KCl is really adding a common ion, this is now a Le Chatelier's problem. This is now a stress. Now, I don't care how you think about it. The easiest way is say, hey, this is what we do. Stress. The stress is we increased, brackets, represents molarity. We increased the chloride concentration. We added KCl, who dissociated, broke apart into free chloride ions because it's soluble. The response is what the chemical reaction will do in order to move back toward equilibrium. So, let's say we're in equilibrium, we're right here. Let's say I dumped KCl, like I did yesterday, in one of those reactions. I'm putting more products than allowable by nature. So I was here, and all of a sudden now I'm here. I'm now there. And what do we know? The reaction is going to move toward equilibrium. The reaction is going to shift where? To the Beyonce, to the left. The reaction shifts to the left. I don't care if you don't like the U diagram. Here's the easiest way to do it. Hey, we increase Cl. That means that we always respond by doing the opposite to regain our balance. So we're going to what? It's going to shift in order to decrease Cl. You can only go left or right. If I go this way, aren't I producing more Cl negative? This is a reactant product, and that would not what we want. If I go shift to the left, which is the answer, I'm using up these two to make this. We've got to decrease. So whether you use a U diagram or you use this chart, they're the same thing. And what did it mean? It means that the reverse process or pathway has now increased. And if the reverse process has an increased ability to go in the reverse. Nature, the environment, the universe is allowing now a pathway in the reverse that wasn't. What does that do to the forward? It has to be less. The forward spontaneity. Spontaneity is a measure of your direction. So if your reverse is increasing in ability, it's going to compromise your forward. Okay? So in any case, this shifts to the left. Now, if this, and it's not, if this was a redox reaction, and it's not, right? Isn't silver +1 here in the compound? Isn't this -1? The charges aren't changing. But let's pretend I'm a princess and this was a reaction that was in a Voltaic cell. The princess part I know is hard. But let's pretend that this was in a reaction in a Voltaic cell. What would happen to the voltage if I made it go shift to the left?
It would go down.
It would go down. Redox in a Voltaic cell is always written with that arrow. We never write a battery with a double arrow. If it did, the battery's dead. Guys, we're going to design a battery that's dead and useless. Good job. No, we want to design a battery that goes to the left. Why? To the right. Because we want zinc, who's really good at what? Oxidizing, with copper, who's really good at reducing, to what? Push the electrons this way, to pull electrons this way. So this is positive volts. If I have an arrow for a redox going opposite that, negative volts. Because guess what? Voltage measures spontaneity, measures direction. When you have a positive volts, that tells you the battery's working really well, right? If you get a high positive volts for your reduction potential, that means the guy's really good at reducing. The size of your voltage is telling you your pathway for the forward. If I got a Voltaic cell with positive volts, I know there's a preferred voltage. But as the voltage drops, I'm getting closer and closer to what? Equilibrium. And by the way, if the voltage goes negative, it's a reversible battery. And you plug it in to go opposite to make it happen. Okay? So back to the problem. The addition of KCl to the system will cause a shift in equilibrium. Well, KCl is really chloride ions. You have to have that visual. So we're increasing the chloride ions. The reaction is going to shift to lower them. And that means you're going to use them up. Now that means that these become the reactants. Go away from the arrow to lower. Okay, so we're going to shift to the left. Good. And the concentration will increase. No. If I shift to the left, you're going to use up these guys. They're on the same team. These have to react to do this. And guys, it's so logical. I know I'm throwing a lot at you, but it's not something you have to memorize. Think with me for a second. How does silver plus hook up with chloride negative? Can you just give me an idea how that might happen? How in the world do I make it precipitate? Don't they have to collide? Right. Right now, separate guys, they got to collide. And when they collide, they stick together. They're magnets, okay? But the point is, they've got to physically collide and say, whoa! I want to make it precipitate and start building a crystal. If I add more chlorides to the existing silvers, isn't there a greater chance of collisions? If there's more of these chlorides, won't the silver more easily find the chloride ions? Sure. That's why there's a better pathway in the reverse. Okay? So, in any case, we're going to go to the left, and the concentration of silver ions will decrease because we're shifting this way. We're making the reverse pathway better. That means these guys get used up, okay, and you make more of that. Here's another way I can phrase this, and you need to understand this. What happens to the solubility of silver chloride? What happens to the solubility of silver chloride if I was to add more KCl? Decrease. Solubility is a word that measures how well a solid ionic compound breaks apart into its ions. Right? So because we're forcing, and this is what's happening here, pay attention, okay? We're forcing, forget this arrow. We have a greater ability now of these guys to become a precipitate. So the precipitate is doing what? Building up faster than the precipitate's dissolving. So the amount of solid is increasing. Party people, we are limiting its ability to do this by going in the opposite, increasing the pathway. So as the reverse reaction increases, the forward process spontaneity or direction gets what? Compromised. So its ability to dissolve into ions decreases by doing this. Okay? And by the way, this is how water softeners work. In our water, okay, we have, especially on Long Island, we have hard water. Magnesium ions and calcium ions in our water. Now, you know this because if you clean your showers or if you're in a bathtub or whatever, if you use a soap, okay, like for your body, as opposed to anything else, but if you use soap, this in the water makes precipitates with the soap. And that's what kind of coats the shower. It's a precipitate. It's like a hard to remove. Because this +2 attracts pieces that are negative in the soap. And they stick together as a precipitate. They call it soap scum. Okay? Now, also in our hair feels different because of those ions. If you use hair products like I do, sometimes it's heavier on your hair. If you ever wash your hair like in New England, you feel different. The hair does different things because you have less of those ions. Any case, okay, people don't like hard water, okay? So what they do is they run the water, okay, and they collect these. You know how they collect them? They add common ions that precipitates them out. And so they add a common ion that these precipitate, and they collect it as a solid, okay? So it's the same idea. We decrease their solubility. Okay. Now, let's look at and apply this to our Danielle cell. Okay? So in our Danielle cell, we have a beaker here and a beaker here. And this is the same demo I've been doing the last couple of days. I've got a zinc metal. I've got copper metal. I have them leaning to the side because I'm artsy. Okay? I have zinc nitrate here, which just means I have zinc +2 already in solution and nitrates. I have copper nitrate as well. And that's copper +2 plus nitrates as well. We have ourselves a salt bridge. You have to have a salt bridge. Christmas in July, that was poorly planned. Feel bad now, I'm over it. Salt bridge. In that salt bridge I have sodium plus ions and I have nitrate ions. Okay, we're going to connect these guys here. This could be a voltmeter. And we're ready to rock and roll. What happens on this side? Well, we know zinc is better at oxidizing than copper. So it's the anode. This is the cathode. And you say, Mr. Grodsky, how do I know zinc is better? How do I know? How do I know? I don't know, how do I get out of this thing? Ah, here we go. I go to my what? Standard reduction potential table. Maybe. Here we go. And I look. And I look for zinc compared to copper. We've done this before. Not the first time. So zinc doesn't like to what? Zinc +2 doesn't like to reduce. It's -0.76. That means zinc likes to what? Oxidize, +0.76. Whereas copper, it's above. Copper +2 actually likes to reduce, which means copper Oxidizing is negative 0.34. These metals are better at oxidizing as you go down. That's how you do it. Now, we know that the zinc becomes zinc plus 2 and sends 2 electrons this way. And electrons always flow from anode to cathode. Why? They always flow from the one who is losing, oxidizing Leo, to one that's gaining. Okay? Who is losing specifically? Well, the zinc 0 is becoming zinc plus 2 and has to lose 2 electrons. Who specifically is gaining? Hey, the copper plus 2 is gaining 2 electrons, become copper 0. This one is getting smaller as it becomes zinc plus 2. And this is becoming pure copper is getting bigger. Remember, metals that are 0 are pure solids. Now, charges. You have to have charges for tomorrow or Thursday. The anode is always negative in a voltaic cell. Why? It's the place where electrons are coming out of. Where are these electrons? The zinc, which is 0, is losing 2 electrons to become zinc plus 2, and it's pushing those electrons through the wire. Remember, voltage is an energy source to push charge around. All right? The copper plus 2 in solution is pulling them, and the copper plus 2 gains those 2 electrons. So you've got to know anode to cathode. Now the cathode is given a positive. No one discovered the anode was negative. No one said, oh, I see in the microscope the anode's negative. No one discovered that. We write negative to say, hey, that's the place where electrons come from. No one discovered electrons were negative either, or protons positive. They just knew that protons and positive had opposite charges. They just, by convention, gave electrons negative. Okay? So it's important you realize that. Okay. Salt bridge is necessary. Pull the salt bridge out, battery goes dead. Okay? What's it do? Over here, I'm producing zinc plus 2. This beaker's getting positive. How could electrons leave something that's positive? They'd be attracted to it. So party people, I need something to keep this beaker from getting too positive. The negative ion comes running down. I expect you to know what ion in the salt bridge. And I will tell you this. In this salt bridge, I've got what? Sodium nitrate. I'm not going to tell you it's Na plus NO3. You should be able to figure that out. Metal in front screams an ionic compound. The only difference here is that the ion is a cluster called a polyatomic ion. Over here, we're losing the copper plus 2 as it becomes copper 0. So we're losing positive in this beaker, so this beaker is getting negative. Why would electrons who are negative move to negative? They won't. They repel that. So we got to replace the positive that's lost to keep it electrically neutral. The positive runs down that side. Okay? What's the job of the salt bridge? To allow ions to flow to keep these beakers electrically neutral. Okay? All right. Let's add a stress. All right? Let's add a stress. Now, the stress I'm going to add is I'm going to add sodium sulfide. And I'm going to add that to this beaker. I'm going to add sodium sulfide to this beaker. Now, sodium sulfide. I got a metal in front. What is it really? Crystal. Made up of what? Na plus. Now what's the charge of sulfur, you think? Needs 2 electrons to become stable. Negative. Or, the first step in redox was to assign oxidation numbers, right? Sodium is a group 1, has to be plus 1. There's 2 of them, right? Plus 2 overall. Whole thing has to equal 0. So this negative side has to be negative 2, and since there's only 1 sulfur, it's negative 2 individually. Right? So, sodium sulfide party people, when it hits the water, do you think sodium sulfide's soluble? Based on your solubility rules? Is sodium on a group 1 metal? Is sodium a group 1 metal? Yes. So here are solubility rules. Group 1 metals are always soluble. So no, I don't care what the second part is. Like Coulomb's law, low charges. So this breaks apart into what? It breaks apart into sodium ions, 2 of them, and 1 what? Okay, now, is there any sodium in the overall reaction?
Yeah.
Where?
Oh, sorry, I meant
No.
in the salt bridge.
Yeah, in a salt bridge, right? But the salt bridge are spectator ions. They're not part of the reaction. So I'm not adding anything that's common in terms of the sodium. Is there any sulfur ions in the overall reaction? Okay, so this is not a common ion problem. This is not a common ion problem. I didn't add something that was common. But what do I know? Last night's homework. You are delivering a -2 ion. -2, what's Coulomb's law? Size of the charge increases the size of the force of attraction. If the positive and negative stick together better than water can pull them apart, it's going to make a crystal. Yes? Okay. It's going to possibly make a what? What's the word I'm looking for?
Precipitate.
That's right. Excellent job. Excellent job. Yesterday in class, you guys are home, I added a carbonate ion that was -2. Here I'm adding an S -2. So when I drop in this beaker, this S -2, okay, is going to attract this +2. And what you're going to make, party people, is you're going to make copper sulfide. Can you guess its phase? +2 and a -2 stick together. Water can't compete. You're going to make a solid. And that solid, you're going to start building up on the bottom. And if it's building up on the bottom, the copper +2, even though it's in a crystal, has no ability to get to the cathode to grab electrons. So, party people, this is not a common ion, but by adding and delivering an ion that precipitates, we are in fact doing what to the copper +2? Are we increasing its concentration or decreasing it? What are we doing to the copper +2 by delivering sodium sulfide into this reduction cell? Are we increasing the copper +2 available for the reaction, or are we increasing it, or doing nothing? We're locking up the copper +2 with the sulfide into a crystal. There is more or less copper +2 ions in solution. That's right. The copper +2 in solution, there's less of them because a lot of them now are going to hook up with the S -2 to make copper sulfide. And if it's a precipitate, that means the ions are not flying around freely anymore, which means they can't hit the copper electrode to pull electrons. So you can, by logic, figure out what's going to happen. Yes?
What happens to the Na+1?
Well, in truth, it may flow through the salt bridge or help with electrical neutrality, but it does nothing in terms of the overall reaction because it's not part of it. It spectates. It may move around and help, by adding sodium here, you may help the salt bridge out to keep electrical neutrality, but electrical neutrality has nothing to do with voltages. Voltage is a directional pathway. So, what do we have? We can do this 2 ways. We have the stress and the response. By adding an ion that will precipitate, we are going to lower the copper +2 concentration. The response is always opposite to regain its balance. Now, in truth, what it's doing is regaining its equilibrium or moving toward equilibrium. So the response is to make more copper plus 2. Which direction would that shift have to be to make the response what the reaction needs? Terribly worded. Where would the shift in this reaction be to increase the copper plus 2?
Left.
To the left, right. You'd have to shift this way for that to happen. Now you know I'm not happy until I draw a U diagram, until you guys get it. So here it is. Okay? Sorry, but I'm going to keep doing it. Reactants, products, death of a reaction. Now, in truth, this was going. This reaction was going, so we were like right here. So we were moving toward equilibrium, and we were definitely spontaneous because we had positive volts. Let's actually make it here, higher. My bad Grodsky, good pizza. So we're like right here. And this thing was really going forward, positive volts. Now, by us lowering the copper plus 2, we are increasing the directionality pathway of going in the reverse. We are making the reverse more of a possibility. We're increasing the pathway of the reverse, which means I'm doing what to the forwards? Spontaneity or directional pathway. I'm limiting it. And so it does go down. So this is positive volts here. And by it going in reverse a little more than forward, this drops to, let's say, right here. Look at this arrow to equilibrium. Not as spontaneous. The volts drop. Why would it move down? Because the products now are favored. If you lower the reactants, the products become more favored. And now you're closer to equilibrium, you're not as spontaneous, your voltage drops. I don't care how you think about it. Redox reactions want to go this way. You force them opposite, the voltage which is a measure of what? The pathway of the forward has to drop. The battery is going to be dying. Okay, yes?
Like for the answer though, would you say it's like just less spontaneous or it's going
You could say,
left?
well, you could say less spontaneous because the voltage drop, because you're giving a pathway for the reverse. So many great ways to talk about it. You don't have to do all of that, but I'm trying to make you understand all of it. So it's definitely the forward reaction is less spontaneous. What does that mean? The direction for the forward direction is not as great because it's being compromised because we're increasing the possibility of the reverse.
But it's still forward.
It's still forward because we're not at equilibrium. Okay? But eventually, we could change, if we added enough of this, if we added enough sulfur to hit every copper, the voltage would go to 0. Okay? Bottom line is the voltage drops because we are increasing the reverse pathway, making the forward, which is measured in positive volts, less able to go forward. Okay? And that's an example of precipitation. Okay? So those are two things. How did I do this a couple days ago? I did the same thing by pouring water. Okay? If I poured water into this one, I would dilute the concentration. Except what I did a couple days ago is I poured water into this one. What did I do? I poured water so that I lowered the zinc plus 2 concentration. I diluted it. It wanted to do what? Make more zinc plus 2. Shifted that way. And now you're going to increase the voltage. Okay? All right. So that is pretty much all the skills that covers. Now there's one piece to this I want to review and then we'll give you the break. Let's look at it, your homework. Oh, Christmas. Homework was the skills key, right? One of the works. Where are you? Stay with me. I was all good until I did that. Oh, here we go. Okay, let's look at this for a second. I know there's a lot going on here. Okay, let's look at iron and chromium. How do I know that iron? How do I know that chromium was the anode? I go to the standard reduction potential table. I made it simplified. Who's more negative? Chromium. Chromium is like their what? Reduce, So it's the chromium likes to oxidize. So this one, just like my zinc was lower than iron. Chromium's lower than my zinc was lower than copper. Here, chromium's lower here. So there's my anode. Iron is my cathode. Okay? Now, this is a point I want to make. When you do these half reactions, chromium's going to chromium plus 3. Okay? That means there's 3 electrons given off. It's oxidizing, right? Its charge is going up because it's losing negatives. The Fe plus 2 has to go to Fe0. Solid is becoming aqueous ions. Aqueous is becoming solid, but this has to gain 2 electrons. So this is gaining 2 electrons, is losing 3. You can't write half reactions where the electrons are unbalanced. I haven't covered this in class, so I'm just talking about it today. To make sure that you balance your half reaction, you must, what's the common factor between 3 and 2? 6, right? So how do I make both 6? I multiply by 2 all the way across, then I multiply by 3 all the way across. And now my electrons cancel. They both have 6. And then I take these numbers, and they become my overall when I put them together. And one nice check for an overall is to make sure your charges are the same. Whole conservation of charge. Now, this is important. This is a mistake someone's going to make tomorrow or the next day. Hopefully not you guys. This value for oxidation is always the what? The reverse of what's in the table. Okay? The one for reduction is as written. But wait a minute, Mr. Grodsky. You multiplied this by 2 to get 6 electrons. Should I multiply this by 2? No! We never multiply voltages. Never, never, never multiply voltages. A voltage measures the ability of the chemical to either oxidize or reduce. It has nothing to do with how many electrons are being passed around. When I say chromium is positive 0.74, we're talking about the ability of chromium to become plus 3 because it does what? It's good at giving off electrons. Its ability to do what? Push the charge around. And we measure the ability of the reduction of Fe plus 2, its ability to do what? To pull. In fact, it's not that good because it's negative. Having more or less electrons does not mess with the individual ability. Voltage is about the pathway in pushing and pulling based upon the abilities of the individual oxidizers and reducers. The number of electrons measures current. Current is how much water flowing. That's not voltage. Amperage is current. How much electrons are actually flowing? Voltage is the power due to the individual chemicals and pulling and pushing. Notice Fe plus 2 isn't really good at reducing. It's negative reduction potential. How did this become positive? This was strong enough to overcome that negative. Okay, so never multiply these by the values here to get electrons. These are individual these are about what? Pathways that are possible due to their abilities. People are going to make that mistake. Okay, and then that's really everything here. Okay, so notice in my sodium bromide, this is reduction. Reduction means I'm losing the positive as it becomes solid, so the positive has to replace that. Here, I'm producing chromium plus 3 as a solid oxidizes, so I need a negative to balance it, all right? So that covers all your skills, okay? And so tomorrow you're gonna get something just like this. 2 metals, write the half reactions, balance electrons, give me the overall, get the voltages right. The oxidation one is flipped, right, because it's written as reduction. Do the flow of electrons, flow of the charges, and then I'm going to ask you a question about the stress. We're going to add something. It could be a common ion. It could be something delivering what? That precipitates out. All right?